This is Team Gary coming to you live on recording. Science 9. Anyways, we are just polishing off the lab before we look at some other things about current electricity. This lab, which we did yesterday, and we're just wrapping up here, attractive or repulsive? We're looking at this question: is there a connection between current electricity and magnetism? And we've discovered there is. So we've stated that as a purpose in your own words, usually with the phrase to find out or to determine, and then translate the question into a statement called a purpose. Just use a battery, alligator clips, rubber bands, and such, and ran it across our compass magnet, and we discovered that, yes, there is a connection. Every time you run the electrical current running through the wire, it flipped the needle. I don't recall, actually. It would have depended on which way you have the battery. Your group probably. The fact is, though, that you had something going, right? Okay. There's actually something called the right-hand rule about the direction of a current going through. I'll stop because you can see me. The other thing we did, and I had a bunch of people, you couldn't see it because I had to get 4 or 5 of you to hold batteries together to make a long chain. And it's not that impressive, but maybe I'll take it off next year. The iron filings were somewhat, not strongly attracted to, because it's not a strong current that we had going through there. It was a stronger current, definitely. But they were somewhat affected by the magnetic field created through this. Not that I need. What did we observe? Just as you can put this down here for the. We observed a slight attraction. The iron filings were. It wasn't strong because we have pretty weak batteries. They've been used for a few years. A weak attraction to the line with current running through it. Maybe say that for the iron filings. You might just label it 3. I'll just put 3 there. I think you guys can handle creating a sentence that answers observation, right? There we go. Okay. There was an attraction. Maybe add in a weak attraction. Or the iron filings to the wire, current running through it. We do experiments, labs, hopefully to answer questions. Sometimes it's just to confirm something that you thought. A conclusion. One of my fancy seats. Then I'll pray for you. I remember. I was going to do all out handling. I want to do that. Okay. Conclusion. Our purpose was determine if there is a connection between current electricity and magnetism. So, I think our conclusion should directly address the purpose. What's a good starting sentence? Observed, or just there is a connection. Just a second here. Let's get a phrase though that pays big bucks. There is a magnetic field created by electrical current running through wire. How's that sound? Does that directly address the purpose? No. There is a magnetic field created by. Okay, continue on. A wire with current electricity running through it. There is. This one was more of an observation on a measurement lab. And in this case, I think we can let it just sit with a one-sentence conclusion. I usually want a longer conclusion, but Okay, so people have that down. Are you more or less caught up? I know you didn't see it, but more or less you're caught up on this lab. Yeah, I'm not surprised. That's we'll get you. I've been zipping back and forth. So, okay, we're going to take some notes about voltage, current, and resistance. So a little bit of book work before we get into more lab work. You've got this title. So we're done with static electricity for the moment, right? This is current electricity. It means there's movement of electrons. What do you guys already know about voltage? You've heard the word. So what do you know about voltage? Yeah. Lightning strike. Good. Okay. It's associated with it. A source of power will have a voltage given to it. Yeah. Yeah. So we have some vague idea. It has something to do with maybe the energy delivered, something like that. That I'm just putting words into your mouth because I know you. So we have a vague idea. You've heard of voltage. You really don't know much about it, do you? You probably know that high voltage is more dangerous than low voltage in most situations. You can have extremely high voltage though in certain conditions that doesn't happen. How much voltage is involved with a static shock sometimes, for example? Don't know, you guys might say. Because, okay, how about the word current when it talking about it with electricity? What do we know about current? If anything, you've heard of it. Only because I said it, maybe, but have you heard about current with electricity? Okay, what's current mean when you're talking about a river? Flowing. It talks about how fast something's flowing. And that's a pretty good translation into electricity, how fast the electricity is flowing. We know that positives don't move and electrons do, the negative electrons move. So that's actually the parts that are flowing, or the current in electricity. But to think of it as the electrons being delivered so much, it isn't always that. Anyways, it's the negative charge, how it moves around the circuit. Then, resistance. I don't know that you know much about resistance and electricity. Most people don't entirely. You're just writing down the title, but we're just brainstorming or whatever, just seeing what we do know already. Anybody know anything about resistance in electricity? Okay. How about as a word, not to do with electricity? What does resistance mean? How hard it is? Cameron, could you add to that? Because I think that's a good start. How hard it is. Not wanting to, what's that? Exactly, not wanting to do something. That's great. So if you have a flow of electricity and there's a part where it doesn't flow as well through it, that's called resistance. So maybe, and old school light bulbs are easier to understand. When I say old school, like the kind with what we call a filament, tungsten filament. You don't buy them anymore. They were phased out when you guys were young. You can still buy them, I think, if you hunt them down. Tungsten is a particular metal. No, it isn't actually. It's a very light. Well, I've never had a big chunk of it. The parts that are in the light bulb, I should speak, are very thin and light. Anyways, it has a different resistance than copper will. And it's just perfect. And Thomas Edison was the inventor who experimented with all kinds of materials. So he found the right one. Yeah, that rattles. Um, that it creates enough resistance that the metal portion glows, and he could use that to light up rooms, old light bulbs. We've got fluorescent lights in here. You guys got LED now and stuff like that. Anyways, so we don't tend to use it, but it's a very easy one to understand what resistance is. And when we played with light bulbs with the battery, that was a resistance across the tungsten filament that made it glow. More about that later. Okay. So this is the textbook. Don't worry about why I have some larger than others. I'll maybe make this. We're not going to use the textbook right now. I've got it used. Okay. I should maybe make them all the same size. But what did I use? 36. Okay, I'm going to talk to you about some of this. But there, I got organized better. We read it in a couple chunks, but you know what? This year I'm not going to read. So here we are. What you're going to do is jot a few things down here. We might look back in the textbook, and that's why you're writing down the textbook reference pages. Okay? I'm going to pause this while I update a pen. I think we've heard of fuel cells before, maybe. Maybe you guys don't pay attention to the news and stuff. Hydrogen fuel cells. Use hydrogen to make energy, and the waste products are heat and water. Water vapor. Vapor just means gas. And then I mentioned this too. Current electricity, we should have this down on paper. Electricity due to a flow of electrons. And that there's two conditions that must be met. Can I push off the fuel cell part? No. Nope, not yet. What are these conditions that must be met? You need it. Hey, we kind of knew this. We had it in a third thing then too, that you must have something to use the energy, but you need an energy source. A battery is an example that we use. And you need to complete the circuit for electrons to travel, for current electricity to work. The third thing we said, but it's not entirely necessary, but for you to know it's going on. Something to use that energy, like a light bulb or a radio or something. Boy, I'm getting the messages here, those things. So, jot this down, two conditions, right? Pause the video while you jot it down. Okay. Electric circuits, three things. Energy source, a conductor, that's the wire, and a load. And that's what we were referring to with the light bulb thing. The load would be something, oh, it's right there. A load is a device that uses the energy to do a job. Conductors are materials that let electricity pass through it easily. The best example, the most common example is copper wire. It's not necessarily the best conducting metal, it's very good, but it's also very cheap. Gold is really good, but I think for obvious reasons, there's a couple obvious reasons, we don't use it. It's expensive. The other one is that it's quite soft. I'll ask you a question about gold after a minute. For cost and strength reasons, the combination of copper provides, it's quite strong. It's very bendable though too, so you can go around corners in your walls and stuff like this. But it doesn't break when you bend it. And it's relatively cheap compared to other metals. Easy to find. There's plenty of it on the Earth's surface, or on the Earth. You have to mine it to the surface. Thank you. It's pretty darn good. I mentioned gold is a good conductor. You don't use it, it's soft, it breaks apart, and it's really expensive. What do you know about gold, though? How is it? You've probably heard some kind of measurement about how pure your gold is. What's pure gold? Carats. What's pure gold? 2,000, 24 karat gold. Magic. 24 karat magic. You know what I'm saying? Anyways. So if you have 10 karat gold, 12 karat gold, it's a fraction out of 12 karat gold would be half gold. Often, if it's the yellow gold and stuff, it's copper. It can be mixed with other things. But copper and gold is actually a combination that's kind of strong and useful for jewelry. Anyways, so I was just wondering if anyone has ever had gold soup. Gold soup. It's delicious. No, gold soup. You just start with 24 carats. That's it. Aurelia? You're going to tell me that? 24 carats. That's all you need to make gold soup. Okay. We talked about voltage a little bit. We weren't quite sure what it is. I'm going to get you guys to write down this as an explanation right now, and we'll talk more about it as the unit goes on. And I'm going to bring up something on the textbook. What we're going to do is I'll bring up the textbook on the board. Now, my handwriting leaves something to be desired, so I'm going to just try how electrons transfer energy. I'm going to just change that to, wow, that's super huge, though. So we're going to get that, though. I see it didn't quite read my handwriting. First of all, I'll get it to a decent size here. 36 is good. Then I'll actually make how electrons, I don't think I saved it, transfer energy. I just go with this. How electrons transfer energy. And we're summarizing from page 238, 230. I'll just do it this. We're going to do it together. You see, the last time I was teaching, those guys really liked my handwriting, so I'd handwrite a lot. I haven't gotten that feedback from you guys, so that's fine. Everybody's different. Okay, I'm going to bring up that textbook page, 238, 239, and we're going to just read as a group, okay? So page 238, 239, you don't need your textbook. I just want you guys to listen and absorb some things. We'll chat it up. Now, we've already written something down about voltage, but a little bit more if you listen. Don't write everything up. Do not. Each electron in a conductor, such as a copper wire, has electrical energy stored within it. When the conductor is connected to an energy source, the electrons flow through it. The energy source provides more energy to each electron, which enables them to move through the conductor. So there's already energy in the electrons, but the source, like a battery or a plug-in, just juices it up even more. And the difference in electrical energy between 2 points in a circuit is called the voltage. We're going to measure it with a little meter volt. And the higher the voltage in a circuit, the greater the stored electrical energy that is provided to each electron. So it's the energy delivered by an electron is really kind of like what measuring voltage. Well, voltage is used. It has to be between 2 points. Now, how electrons transfer energy in a circuit. When you turn on a light switch on a wall, you close a circuit. It's basically like, you know how we had the alligator clip in the wire? That's basically the idea. It's got a switch and just pushes a piece of metal into another one. The light comes on immediately. How does the electrical charge get from the switch to the light bulb so fast? Magic? Nope. It may surprise you to learn that individual electrons don't travel from the switch to the bulb when it's turned on. Picture electrons in a wire as being like water in the water pipes in your house. And we use water flow analogies a lot because you can visualize this and you have experience with water flow. The water pipes are normally full of water, so when you turn the tap on, you got water coming out immediately. I think that makes sense, right? Not like water from Buffalo Pound gets here and in 1 second, right? When you turn on the tap. Just like the energy from the electrons are already sitting in the wire, right? Okay, now, this is simplified too. And if you study electricity more and you become a physics student in university, or an engineering student, more likely actually that would study it that way, or an electrician, you'll learn more complex, abstract ways of understanding. Electrons in a wire work in a similar way. When an energy source is connected to a circuit, electrons in the conductor instantly push or repel other electrons nearby because of their charge. Right? We understand the positive and negative aspect. When one electron moves at one end of the wire, it pushes the next one, which pushes the next one, and so on, right? This process happens instantly. By pushing that first electron, you make the last electron move. That's why when you flip the switch, the light goes on instantly, even though the electrons themselves haven't moved from the switch to the bulb. Okay? current, electricity coming up. Now we're just reading. I got the notes already figured out, so I want you to have a full understanding and then just summarize. Electric current is a measure of the amount of electric charge that passes by a point in a circuit at a given time, in a given time interval. Think of the steady flow of electric current as being like water flowing through a stream. I already mentioned that, right? The water keeps flowing unless its source dries up, same as your battery. As long as the energy source continues, the electrons continue to flow because the current flows in only one direction. That is called direct current. That's what's provided by a battery, DC electricity. The current that flows through cords plugged into the wall sockets of your home is called alternating current. It does the same job, but it works a little differently. It flows back and forth, back and forth, back, okay, at regular intervals called cycles. This is the current that comes from generators and is carried by the power lines to your home. Sometimes you can convert alternating current energy into direct current energy if it's needed. To measure current, we use something called an ammeter. And that's the unit that we measure. The unit of electrical current is called the ampere. And it's a measure of the amount of charge moving past the point in the circuit every second. Now, nobody talks about amperes, but have you heard of amps on a battery? When you learn to drive, and if you actually have to buy a car battery, you will be told it's a 12-volt battery. But you can actually, like we can use those batteries in the box, those D cells, put a few together, 4 of them together, and get a 12-volt battery. That's not going to start a car because there's not enough current. And they call it amps, is usually, we don't just say amperes. Anybody hear of amps in a battery? No? You have. Okay. So the higher your amps, the quicker the energy is delivered, and you can turn a car engine over into cold with a good cranking, with the high cranking amps, they say, stuff like this. That's what you're looking for in a battery. And if you have a big truck, you want high amp battery compared to my little Toyota car. It doesn't have as much to do. Now, here's some examples. You got digital meters, you got old school meters. We tend to use these ones. Yeah, they're just fine for what we do. They're cheap, they don't require batteries. So back to this. You know what I'm gonna do with this handwriting. So, I'll see if it even reads this. Burnt, current. Okay, I'm gonna just start typing it, okay? Won't even try. So, current. Measure how much electric charge is flowing at okay. Get rid of the handwriting part of it. Oh, son of a sea cook there. Okay, back to this. Did I? It doesn't. I sure did. It's a spacing issue. Did I? 6 brownie points. Actually, 3 points for Hufflepuff. You're Hufflepuff. I have the sorting hat. I showed you guys. Right? And you are a Hufflepuff, right? And what's weird about this? It's a good documentary. What was weird is that I talked about it before you watched it as well. Okay, there's 2 types, and we're going to talk about direct current. I'm going to just type it. Why am I going to move this? I'm sorry, what was that, Shane? Yeah, this is just a continuation. You're going to have quite a bit of notes over the next little while. Okay. I'm just going to grab this so I can read it while I type, and you guys can read it. I'll just move. I know. Well, you do, don't you? You got to be old like me or your parents. Old and lame, man. But we're likable. The parents are, or the people who take care of you. Okay, we'll probably stop here because the bell's going to ring. And just because I had a request, what's going to happen if I change this to read my handwriting, right? Now the one, because it's in a circle, definitely won't translate very well. Okay, yeah, I sure did. See what you mean? It's going to see if that even has it. It's working on it. I think it's, oh, yeah, yeah. So I'll change that. Right current, yeah, yeah, like, didn't work out well. Good thing I didn't do this. So we're packing her in for the day.